A transaxle is a transmission, axle, and differential housed in one integrated unit. A torque converter is a key element found in a transaxle. Its role involves operating as a fluid dynamics system that facilitates the transfer of angular momentum from a car's engine to its transmission. This process is achieved through the utilization of the pressure gradient produced by rotating the fluid, causing the transmission oil to circulate between the impeller, which is connected to the engine, and the turbine, which is linked to the transmission. Additionally, torque converters are equipped with airfoils that generate torques as the oil moves radially within both the impeller and the turbine components.
There are three main components of a torque converter: the impeller, the turbine, and the stator. The impeller is connected to the engine and welded to the casing of the torque converter. As the impeller accelerates, a pressure gradient is created between the inner and outer radiuses. The high pressure fluid at the outer radius of the impeller is then directed over to the turbine. In the turbine, the fluid is decelerated and redirected back towards the center of the torque converter. The shallow airfoils that can be seen here are used for that redirection and deceleration. In between the turbine and the impeller is the stator. The stator is used to increase the efficiency of the torque converter when the two halves are spinning at different rates. It does this using airfoils that further redirect the fluid as it moves from the turbine back to the impeller. These are the dimensions of our torque converter that will be used in the following calculations.
When we mathematically analyze a torque converter, we make some assumptions and abstractions first. We model the flow as being inviscid because the boundary layers along the surfaces in the torque converter do not dominate the flow behavior, and we model the flow as incompressible because torque converters operate at a low Mach number and a high Reynolds number. Next, we set up a convenient coordinate system which keeps track of flow in the streamwise direction and flow in the direction normal to the streamline. Using this coordinate system, we apply Euler's equation in the normal direction to the flow inside of our torque converter. This equation tells us that curvature in our streamlines is related to a change in the hydrostatic constant K. Consider the case where the impeller and the turbine are rotating at the same angular velocity. The streamlines we get are concentric circles, so Euler's equation tells us that the hydrostatic constant is increasing as the radius of those concentric circles increases. Let's consider the equation for the hydrostatic constant, which is K equals P plus rho gz. Since the torque converter is small, we assume that gravity is not dominating the behavior of the flow, so we know that a gradient of the hydrostatic constant must be related to a pressure gradient. In this case, where the impeller and the turbine are rotating at the same rate, the flow behaves as a solid body rotation, so we can use this equation for pressure distribution in fluid rotating as a solid body to analyze our torque converter. Using this equation, an arbitrary rotation rate of 2000 RPM, the density of common transmission fluid, and the specific dimensions of our torque converter, we find that the pressure delta from the inner to the outer radius of our torque converter would be around 500 kilopascals at this rotation rate, which is on the higher end of what the water pressure might be out of a garden hose. However, the interesting thing about torque converters is what happens when the impeller and the turbine are not rotating at the same rate. Using the same pressure distribution idea and equation, we see that the two sides rotating at different rates would cause asymmetric pressure distributions. This causes poloidal motion of the fluid in addition to the toroidal motion, as momentum is transferred from the high pressure side to the low pressure side, and fluid moves from the outside of the faster half around and through the inside of the slower half back to the faster half.
In this section, we will analyze how working fluid properties affect the performance of the torque converter. A primary goal of the working fluid is to transfer momentum while limiting shaft power that is converted to thermal energy. This is accomplished by choosing a fluid with a low viscosity and high density, known as a low kinematic viscosity. This quantity is inversely proportional to the Reynolds number, which drives the Darcy friction factor of the system according to the Moody chart. A good working fluid must be designed to be insensitive to a large temperature range. Variations in viscosity will alter the efficiency of the torque converter, leading to different steady-state errors in impeller to turbine speeds. Additionally, if a fluid heats up and becomes less dense, this affects the net angular momentum transfer, and the RPM will have to increase to achieve the same pressure gradient inside the torus. Since engine speeds are generally fixed, this will lead to a smaller pressure gradient, causing slower transient response times and acceleration. For this reason, transmission oil has been designed specifically for its temperature resilience, low viscosity, and other advantageous properties, such as corrosion resistance, availability, and ability to stain our clothes.